Okay, so as Chairman told, this talk originally should be presented by Konrad Czerski, but somehow he could not attend this meeting and asked to me to present this talk. So I'm not the co-author though. I said yes. Probably this is one of the point of view to the cold fusion study from the nuclear physics side. So therefore, I will present the talk based on his note, but his note came to me very lately. So I just bring in my computer, okay? So the talk now is for accelerator experiment at the lowest possible deuteron energy. It is down to about 4 keV. And extraction to the room energy using several extrapolation, and determine the screening energy. So this is the simple explanation of screening effect. In the figure, you see an interaction potential between an incident particle and a target nucleus. When both of them are positively charged, they repel each other, of course. The bare potential is described in this figure with a black solid line, and its formula is described by black letters in the equation. Just black part. Over here. The most important factor is penetrability, which is presented by the equation PE over here. Let's see. Usually, the target nuclei are surrounded by electrons, which reduce the repulsion force. Therefore, this effect is called screening effect, and the screening potential is plotted with a dotted line in the figure. This one. As well as the red letters in the equation. UV is an approximated screening potential. Penetrability of the charged particle is now changed by replacing E to E plus screening potential. This means that the energy of the relative motion effectively increased, and the reaction probability gets enhanced very much. So this is his laboratory. The group of Czerski has developed a new accelerator facility at the University of Szczecin. The upper photo shows the ECR ion source, which can provide low emittance, high current light ions. They call it UHV. The lower photo shows an equipment for electron Auger spectroscopy for material diagnostic. This shows schematically the experimental setup. The upper left figure shows a scattering chamber, inside of which they placed 4 silicon detectors to measure angular distributions of charged particles emitted by deuteron beam bombardment. The beam comes from this way to hit a target, and then charged particle emitted and detected by these detectors. The lower left figure shows the energy spectra of emitted charged particles. You see proton, triton, and helium-3 particles are clearly seen as sharp peaks. Measured angular distribution is not isotropic, but anisotropic. Thus, it is fitted by Legendre polynomials as the formula shown as d sigma d omega over here. The upper right figure shows the obtained parameter A2, which is important as a measure of the anisotropic distribution. Here, we show examples of the experimental enhancement curve, which is the ratio of the experimental thick target yield to the theoretical one. The screening energy determines the exponential-like increase towards lower energies. In the figure, yield of the D plus D reaction are plotted as a function of a deuteron incident energy for aluminum, zirconium, and tantalum. The deduced screening energy depends on the target material. They have another experiment for other groups, including ours and German groups. For the gas target experiment, from that gas target experiment, the screening potential is deduced as a 25 plus electron volt. These two figures shows overall comparison of experimentally determined screening energy UE of different target, and also comparison of different deuteron stoichiometry MDX. No particular dependence can be recognized. The left-hand figure shows a correlation between screening potential and MDX. So therefore, we thought the results probably from the target surface contamination, that is carbon or oxygen or something like that. Here, blue points show our experimental result obtained at similar experimental conditions, that is, under high vacuum conditions, probably small oxygen contamination. In the left figure, we plot the screening energy as a function of atomic number, and in the right figure, plotted are the deduced values of a polarized screening energy as a function of electron gas parameter RS. Plotted with red points are theoretically calculated results. There's a much difference between the experimental result and the calculated result. Experimental screening energy is by a factor of 2 larger than the theoretical curves, which the calculation is the calculation is performed from a self-consistent dielectric function approach. The target material dependence is correctly described as seen in dependence of the electron gas parameter. Here, we show a new experimental result at a new facility using the UHV. And also the new data obtained using OJ electron spectroscopy. It is for determination of target contamination. In the upper figure, the blue curve included only the screening effect, cannot correctly describe the experimental energy dependence. Experimental points for energy below 10 keV are systematically above the curves, whereas the points for energy higher than 10 keV are below the theoretical curve. Here, then, we introduce a resonance. We assume 0 plus threshold resonance with a dominating deuteron partial width. That is almost single particle resonance. The non-resonant flat contribution can be described by 16 transition matrix elements determined from the experiment. The correct shape of the enhancement curve could be obtained due to the destructive interaction between both contributions, which leads to a characteristic pocket shape as plotted with red curve in the left figure. Free parameters are proton width and the screening energy. The phase shift is taken from other experiments. The screening energy of about 100 electrovolts is now very close to the theoretical expectations. Okay. So, here, a new experimental result. Oh, sorry. This. This figure shows the location of the threshold resonance with the red line over here. And the resonance at the excitation energy of about 30 MeV indicated by blue box are known to have 2+ structure. To explain this structure, the additional 0+ threshold resonance has to be assumed. That's why they require the resonance, threshold resonance over here. These plots show the threshold resonance is also necessary to explain the N over neutron over proton branching ratio. Without threshold resonance, you cannot this curve. You can get this curve. And the corresponding angular distributions and also anisotropy are coefficient. Plotting over here and plotting over here. the resonance cross-section is described by the given equations. The resonance curves, that is actually astronomical S-factors for different resonance energies, are shown in the upper figure. For lower energies, the resonance width and the resonance height increase. Both depend on screening energy. However, at the deuteron energy below 1 keV, the deuteron width will be smaller than the electromagnetic width corresponding to electron conversion, internal pair creation, etc. The gamma 0 plus to 0 plus transition to the ground state is not allowed, of course. Therefore, the total width reaches its maximum value and the resonance height will be the largest. Enhancement due to the threshold resonance up to 7 orders of magnitude at just a threshold energy. If you have a resonance over here, the enhancement is 10 to the 7th. The threshold resonance is also important for explanation of the experimental data of the normal deuterium dP Traget measurement on the gas target. It's already reported by 1995. So this is the plot using the introducing the threshold resonance. We see that similar to the metric target, the screening curve cannot describe the data. The red curve is a non-coherent sum of a screening and resonance contribution. So these calculations is done without interference. Here, the enhancement factor was measured by a constant deuteron energy, the fixed incident energy at 15 keV. And to look at the dependence of irradiation time. Usually, we used for the screening energy determination just virgin targets. It's cleaned by an argon beam. So just usually they use the data, just this value. So it means only the first point in the figure. We observe, however, an increase of the enhancement factor for the longer irradiation times, although oxygen contamination remains below 1 atomic monolayer. After 4 hours, the enhancement factor decreases because of large target surface contamination. And then after 22 hours, the enhancement disappears. Measurement at different times corresponding to screening energy ranging between 100 electron volt and 500 electron volt. Crystal defects produced by a small oxygen contamination lead to localization of conduction electrons, and to an increase of effective electron mass, consequently to the increase of the screening energy. Thus, we can change reaction cross-section by changing the electronic structure of the target material. So then we estimate to down the temperature to the room temperature, what the reaction rate goes. So left figure, cross-section and thick target yield of a DP reaction plotting depending on the neutron energy. And right diagram, right figure, the reaction rate at room temperature plotted, and versus let's see, versus screening energy. There's some lines, limits are plotted. The first one is determined by cooling. It's corresponding to deuterium molecule, and Steve Jones measurement neutron emission in electrolysis, and Fleischmann-Pond heat excess in electrolysis. So these are three lines over there. Changing screening potential between 100 and 500 electron volts results in changing of reaction rate at room temperature by 50 orders of magnitude, as you can see. To reach the reaction rate of Fleischmann-Ponds, for example, additional 7 orders of magnitude are needed. From the previous discussion, it can be obtained by the threshold existence of a threshold resonance. Okay, I come to the conclusion. So I can see. So electron energy. Electron screening locally enhanced by impurities and crystal defects. And it can change the reaction rate at the room temperature 40 order of magnitudes by just changing screening potential from, so for example, from 100 electron volt to 500 electron volt. And the important to introduce the 0 plus threshold resonance in helium-4, we should have another 7 orders of magnitude enhancement by introducing this threshold 0 plus threshold resonance just around the threshold. So that is the conclusion. And finally, this is the paper of the experiment. Thank you.
Any questions?
Well, don't ask to me the tough question, because this is not my work.
Very simple, Kasagi, I hope. So, I have seen some correlation between screening potential, this surface effect, and a low working function material is the same surface effect. My feeling that both are strongly correlated. Do you have some idea, comments, or I'm just crazy, as usual?
Well, I have several comments on this work also, but I shouldn't comment this time.
But we are between friends, so okay, you can say what you want.
but you see, his thinking to need another enhancement. He want to put the threshold resonance, and seems to another experiment, for example, gas target experiment, the introducing that kind of resonance also can be explained. That's his point.
Okay, thank you.